Lesson on Coulomb's law. Charge. Charge is to electricity and magnetism as mass is to forces in motion. Recall that we always put in mass when we try to calculate the net force on an object, the kinetic energy of an object, and the momentum of an object. Similarly, whenever we talk about electricity and magnetism concepts, we'll need to use charge. Charge is symbolized by the letter Q. The units of charge are the Coulomb, and named after Charles Auguste Coulomb, pictured right here. Earlier we said the fundamental charge is what a proton and electron possess. This fundamental charge, designated by E, is 1.6 times 10 to the negative 19th coulombs. Why is it not 1 coulomb? Well, that's a topic for another video. The typical amounts of charge are in microcoulombs. That is, very rarely will you encounter a charge of 1 coulomb or greater. And 1 microcoulomb, symbolized by the letter U there, microcoulomb, is equal to 1 times 10 to the negative 6th coulombs. So whenever you see microcoulombs, you'll need to convert that into coulombs to use in our equations. Again, this little mu symbol represents micro. In the static charges video, I showed you how to charge objects either positively or negatively by a number of methods. But what if you wanted to know the number of excess charges on a charged object? Well, you would need to know the total charge on the object and divide it by the fundamental charge to figure out how many excess electrons were on that object. Let's look at this example. Here a conductive sphere has a charge of negative 50 microcoulombs. How many excess electrons are on the sphere? So let's put on the total number of charge, which is 50 microcoulombs, or in other words, 50 times 10 to the minus 6th coulombs. And we'll divide that total amount of charge by the charge of 1 electron, which is the fundamental charge, or 1.6 times 10 to the negative 19th coulombs. Pause the video for a moment and do the calculation and see if you get the right answer. That gives us 3.13 times 10 to the 14th electrons. That's a lot of electrons. Charles Auguste Coulomb published his Coulomb's law in 1784 in his memoirs. This describes the amount of force between two charges. Let's call this charge Q1 and this charge Q2. You notice that the force depends directly on the amounts of charge and inversely on the distance between the charges. He called that distance R. Thus the electric force is equal to a constant of proportionality K times Q1 times Q2 divided by R squared. Notice that the force depends directly on the amount of charge. That is, if Q1 or Q2 becomes larger, the force will also become larger. And if we increase the distance between the charges, the electric force will decrease. That is, the electric force is inversely proportional to the distance between the charges. Conceptual example number 1. Again, let's remember that the force between Q1 and Q2 when they're separated by a distance r is given by Coulomb's law as K Q1 times Q2 over R squared. What happens if the force on one of the charges is doubled? That is, we make Q2 2Q2. Well, the new electric force here is going to be equal to K times Q1, but now times 2Q2. And there's still the same separation, so over R squared. For convenience, let's put the 2 right in front of the K since this is all multiplication. Rewriting this gives us 2 times K times Q1 times Q2 divided by R squared. But look closely. KQ1 Q2 divided by R squared is just the original electric force here when Q1 and Q2 are separated by the distance R. Thus we have 2 times that amount of force now. So we can see the new electric force is 2 times the old electric force. It doubles. And I hope that makes sense, because since the electric force depends directly on charge, if we double one of the charges, that overall force will double as well. In the previous example, we determined what happened to the electric force if one of the charges changes. But what happens to the force if the distance between the charges changes, or in this example, if that distance is doubled. That is, we move charge Q2 twice the distance away from Q1, and we'll call that 2r. Well, let's make a prediction first. We know that electric force depends inversely on the distance between the charges. So if I increase this distance, the electric force should decrease, but by how much if I double the distance? So now we have the new electric force is equal to K Q1 Q2 divided by 2r squared. Well, what is 2r squared? Well, 2r times 2r is 4r squared. So let's put that in the denominator. So now we have the new electric force is K times Q1 Q2 divided by 4r squared. But if we look again, here's our original electric force. It's K Q1 Q2 divided by r squared. So we have an extra 4, or 1/4 here. So we see we have a quarter amount of the original electric force. That is, it decreases by a factor of 4. You will be challenged to do more conceptual examples like this in class and to write out the new electric force in terms of whatever changes about the charge and the distance and comparing it to the original electric force of K Q1 Q2 over r squared. Now that we've completed 2 conceptual examples about how the electric force changes based on changing the charge or distance, let's try a mathematical example to calculate the electric force outright. Here we have a charge of positive 6 microcoulombs separated by a distance of 10 meters with another charge of negative 2 microcoulombs. We're going to use Coulomb's equation, but now we need to calculate, so we need to know what this constant of proportionality is, where K is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. So our units of force will still be newtons, and to keep that true for this equation we need to cancel out the meters from the distance and the coulombs from the charges, and of course those are squared. So let's calculate this. So the electric force will be equal to K, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared, times Q1, which is 6 microcoulombs. But remember, we need to convert that into coulombs. And since a microcoulomb is 10 to the minus 6 coulombs, that makes this 6 times 10 to the minus 6 coulombs. And similarly, negative 2 microcoulombs is negative 2 times 10 to the minus 6 coulombs. We'll divide all that by the distance apart, which is 10 meters, and we have to square that. So pause the video for a moment, do your calculations, be sure to input the exponents correctly into your calculator as well. So on the numerator, I got negative 0.108 Newton meters squared, and the denominator we can see is going to be 10 squared, or 100 meters squared. Completing the calculation, I got negative 1.08 times 10 to the negative 3rd newtons. Now this negative sign just represents that this is an attractive force between the positive 6 microcoulombs and the negative 2 microcoulombs. You could also see if both these charges were positive, I get a positive force. If they were both negative charges, I would also get a positive force, and that would be a repulsive force. Thank you for watching, and see you in class.